Swayam Prabha. Digital India. Educated India.
Then, the way I am drawing. So this is how it is. So I am going to have a fundamental exactly coinciding with the zero crossing of the square wave. So if I look at the square wave versus the sinusoidal waveform, both of them will have the zero crossings coinciding everywhere, positive going, negative going, and so on and so forth. So if I try to look at this voltage, what I have, versus this current, how they are displaced from each other. Please note, the current that was flowing in the supply, which is far from being sinusoidal, was shifted from the original voltage by alpha. If I am firing the thyristor converter at a firing angle of alpha. So this is the phase shift between the current and the voltage. And if I look at this current and the fundamental current, both of them are actually not phase shifted. They are in phase with each other. So I can say the fundamental current and the fundamental voltage are shifted from each other also by an angle of alpha. Right? So this particular angle is generally known as the displacement power factor angle. The displacement power factor angle is the angular difference or the displacement between the fundamental component of the voltage and fundamental component of current. So that is actually going to play a vital role in deciding what is the kind of power factor I can anticipate in my circuit. Because this is essentially pushing the current behind. That angle is telling you how much is the fundamental current being pushed behind. So if this is the way the current is being pushed behind, when I calculate the power, generally we say V times I integral over a cycle and average it over the complete cycle. So obviously, wherever the voltage and current are not in phase, I am going to have some reactive power. That's what is manifesting itself as reactive power. So whenever I am going to have a displacement power factor other than unity, I will have a good amount of reactive power content in my circuit. I can't help but have some amount of reactive power content. Just to reiterate this again, let me draw the waveforms of the fully controlled converter's voltage. So maybe this is the voltage of the fully controlled converter. The current might start at alpha. So it may be alpha to pi plus alpha, and it may come from pi plus alpha to 2 pi plus alpha. So this is alpha, this is pi plus alpha, this is 2 pi plus alpha. And I am going to have this as 0, this as pi, and this as 2 pi. So if I am drawing the fundamental current corresponding to this, I have to draw the fundamental somewhat like this, not to scale. So I am just drawing to establish the zero crossing, that's it. So it is going to be somewhat like this. This is how the fundamental current is going to be. So this is I fundamental, this is IS without incorporating any of the ripples. I have neglected the ripples, and this is V supply. Right? Now whatever is the displacement between the fundamental voltage and fundamental current, between these two, this angle, this is alpha in this case, this is called as displacement power factor angle. And cos of this displacement power factor angle is known as displacement power factor. So I will have essentially this contributing towards rather requirement of reactive power. So the thyristor converters in general have a couple of issues or couple of problems. One problem is always the converter circuit, even if I connect a simple resistance, in all probability I will ask for some amount of reactive power. The circuit will demand some amount of reactive power. Right? So it is going to demand certain amount of reactive power because the displacement power factor is not unity. And the second problem is the currents are far from being perfect sinusoids. There are large number of harmonic content that is present in the current. So if I have lot of harmonic content present in the current, imagine my source, which is a sinusoidal source, all right, but I am going to have some impedance, resistance and so on in the transmission line. If it is a three-phase, everywhere I will have some, transmission line impedances. All these things are going to carry this harmonic current. So R multiplied by that harmonic content of the current will give me some harmonic voltages, whether I like it or not. So there will be lot of harmonic voltage generation. Although my generator, poor fellow, is trying to generate purely sinusoid, I have generated all these harmonics. So whenever I connect an induction motor or anything which requires sinusoidal supply, they are all going to get all these harmonic voltages also injected into them, which is not good for the induction machine, because we analyze the induction motor assuming it's all sinusoidal supply. The moment there is a non-sinusoidal supply, I may have, fifth harmonic, seventh harmonic, third harmonic, 11th harmonic. So I will have different revolving magnetic fields. One rotating at fifth, 5 times omega s, another rotating at 7 times omega s, another rotating at, 11 times omega s. So many things, all of them are going to confuse the hell out of the induction motor. So this essentially is a prelude to power quality. I am not going any more into this, but I am trying to say that power electronic converters are a big menace. They create power factor problem, they create harmonic problems. And the solutions also lie in power electronics ultimately. So we create the problem, we also eliminate the problem ultimately with power electronics. I will not go into any more that. Yes, sir. If I am talking about square wave, that is the current actually drawn by the converter, which I cannot eliminate. Because of that, I will have harmonic currents. And if I have harmonic currents and if I have R and L multiplied by the harmonic current will give me the harmonic voltage drops. So although I generated sinusoid, now I'm going to have some harmonic voltages, maybe negative, maybe positive, whatever, that is generated in the transmission lines, which is ultimately is going to reach the motors and so on, which I'm connecting in the power grid. And these are not 1 kilowatt, 2 kilowatt. Power electronic converters, most of them may be megawatt level. Especially when I talk about DC motor drive or AC motor drive or HVDC transmission and so on and so forth. Everything will be incurring so much of harmonic content into the entire system. Right? So we'll not dwell on this, but on the whole, DPF, that is displacement power factor angle, power factor and so on are extremely important in terms of the overall performance of the thyristor rectifiers. Okay, so much so for single phase. Let us now try to look at three-phase uncontrolled rectifiers. Let me again start with the simplest of configuration, which is a half wave diode rectifier. So let us say I have 1, 2 and 3 phases. These are the three phases. So let me call this as VA, N, this is probably neutral, and this is VB, N, and this is VC, N. Three phase voltages which are 120 degree shifted from each other, and I am assuming balanced voltages. Obviously, all of them are having the same magnitude, right? Peak magnitude is the same. So I am going to have one diode here, second diode here, and third diode here. Let me call this as D1, this as D2, this as D3, right? And then finally from the neutral, I am going to connect a load which is also connected to this star point like this. So what I am converting is AC to DC, of course, and the DC is connected between the neutral and the star point of the three phases which are connected after the device, right? So I have to see at what point D1 will conduct, at what point D2 will conduct, and at what point D3 will conduct. Let's first of all start off with a simple resistance load, R load, right? So let me first of all draw the three phase voltage waveform. So this is the sinusoid. So let me divide this into 120 degrees interval, 60 degree interval. So obviously my second phase is going to be somewhere here, and the third phase is going to be something like this. These are the three phases, right? Now let me name them. This is VA, so the second one is VB, and this third one is VC. Whichever is the diode which is having the maximum positive voltage, hopefully that will conduct. We will come back to the logic as to why that should only conduct. So during this portion, the maximum positive is with this particular phase. During this portion, the maximum positive is with red color waveform. During this portion, the maximum positive will be with green, right? Whatever is the maximum positive, let us say that conducts. So from here to here, I am going to have D1 conducting. From here to here, I am going to have D2 conducting. From here to here, I am going to have D3 conducting, right? Let us say now D1 is conducting. When D1 is conducting, it is as good as a short circuit, right? When D1 is conducting, if I try to look at the voltage across D2 and D3, VAN will come here at this point because D1 is conducting. So this voltage will be VBA, this voltage will be VCA. Do you get my point? Because on one side it is connected to a source. On the other side it is connected to VAN through this conducting diode. The diode is conducting. So entire VAN is applied to the load because this point becomes VAN. So the voltage across this will be VBA, the voltage across this will be VCA. And if I try to look at VBA or VCA, because A is the maximum, VBA as well as VCA have to be negative. There is no other way. The maximum is A. Rest of them are all smaller. So VB minus VA or VC minus VA, all of them have to be negative. There is no other way. So both these diodes are automatically reverse biased. Whenever I am going to have D1 conducting and A phase voltage is the maximum at that point, automatically other two diodes are eliminated. They are not going to be able to conduct anymore. Whereas at this point, because D2 now has the maximum value of voltage, again the same logic holds good. D1 and D3 will automatically be eliminated. Because beyond this point, D2 will get automatically forward biased. Because it gets forward biased, it will jump into conduction. And once it jumps into conduction, you are going to have the other two diodes eliminated automatically. Right? So, I am going to have the voltage for a simple diode rectifier, whether with R load or RL load, it doesn't matter. If it is a diode rectifier, I am essentially going to see that the voltages that come up are this entire thing. I'm going to get this entire thing as the voltage that is coming up across the load. If I try to look at the load voltage, this entire shaded portion comes. So whenever D1 is conducting, I'm going to have the entire VAN. Whenever D2 is conducting, I'm going to have the entire VBN. And similarly, I'm going to have entire VCN whenever D3 is conducting. Right? And please note, this is repeating itself for every 120 degrees. VAN comes up for 120 degrees, VBN comes up for 120 degrees, VCN comes up for 120 degrees. So, I have to essentially get the value of voltage by integrating from this point until this point. When I integrate between these 2 points, that's where D1 is conducting. Right? If I try to integrate the voltage waveform for just 120 degrees, it is sufficient enough. I don't really have to integrate it for the entire duration. So I can simply say, if I assume this to be 0 of omega t, right? This point is 30 degree because I told you that already I had divided everything into 60 degree interval. So this point is 30 degrees. Right? And 30 degree is pi by 6. So, I have to essentially integrate the voltage. So, if I say VDC or V load average will be equal to 30 degree to 150 degrees. Right? And I have to write Vm sin omega t d omega t. Where Vm is phase voltage peak, not line voltage peak, phase voltage peak. So this Vm happens to be phase voltage peak. And I have to average it over 2 pi by 3, exactly. Right? So this is going to be the kind of expression I will get for a 3-phase half-wave rectifier with diode. So it is uncontrolled rectifier. This is just for the sake of continuity. Again, this is hardly ever used anywhere. Because you should know how a half-wave rectifier works. Then we will go to full wave. That's the reason I am kind of discussing this, because this hardly has any applications. Hardly ever. Look at the current now. If it is like a resistance load, I am going to have the current somewhat like this. This will be the current. So it will go like this, and again it will jump up like this. Same 120 degree duration, again I will have the current like this. So this will be the current for R load. For R load, the current will be exactly following whatever is the wave shape of the DC voltage, load voltage. But A phase will conduct only for this duration, B phase will conduct only for this duration, and C phase will conduct only for that particular duration. So we are utilizing each of the phases very limited manner, in a very limited manner. We are going to have A phase current flowing only for 120 degrees. So if I try to draw the current waveform for A phase, I will draw only like this. That's it. This is A phase current. Right? And if I try to draw the current corresponding to B phase, this is going to be B phase current. And again, if I try to draw the voltage current waveform corresponding to C phase, this is going to be C phase current. No negative half cycle currents. And the currents are far from being sinusoidal anyway. So this really gives rise to, again, huge amount of harmonic content and without any negative half cycle, which means saturation of the transformer could be very well seen in this particular kind of rectifier. So this rectifier is really problematic because of these reasons. And one more thing is, without neutral, I can't work in this particular rectifier. And most of our industries will have only 3 phases coming in. You will hardly ever see a neutral. 3 phase will directly come to any industry. If the neutral is not there, you can't use this kind of a half wave rectifier. So this kind of half wave rectifier is hardly ever used in any of the industries. Right? So we'll go over to full wave rectifier in the next class, but I will also try to upload some problems. Thank you.